Hello everyone. Today, this is the week 5 of the problem solving session for deep learning for computer vision. And today in this talk, we will be covering a brief introduction to like convolutional neural network. And then we will see the implementation of Linnet, which is one very basic CNN, which is used for MNIST dataset. MNIST dataset is the one in which we have images of handwritten characters, which has to be classified into one of the 10 possible classes. These images contain characters, basically the digits from 0 to 9. Okay, give me a second. Okay. So, so in the last session, we talked about fully connected networks. And I hope you all remember that in case of fully connected networks, we were taking these images like in the last session. We experimented with MNIST dataset. So the MNIST image was being flattened into a one-dimensional vector and then was given as an input to the dataset, to the network. But what about if the images are very large in size? Like for example, the images of the MNIST data set is 28 cross 28. But if we talk about the images, the real world images, which can be like from 224 cross 224, or it can be like HD images, which is like 1024 cross 1024, and so on. So these images are huge. They are a very large 2D data. So each image is actually a grid of pixel values. And if we go and flatten these images, then it results in a very high dimensional 1D data. So if we work with such an high dimensional 1D data, then the size of the model will be too large and it will be almost will be a very difficult task to get the data to train such a large model, and that too on small machines. Now, so this is one main reason that the images can be seen as a grid of pixel values, which is a very high dimensional data. And then it is difficult to process for a fully connected feed-forward neural network. Now, this is one reason. The another reason is that when we look at the fully connected networks, we lose the spatial information. So what happens, like if we look at this particular image and look at the patch here, which is being bounded by this black square, then this is somewhat spatially correlated. Like all these pixels have a values which are very similar to each other. Please try to join as like on time from next session, so that the presentation can go uninterrupted. Okay, so here if you look at this cat then and look at this particular patch in this square, then all these pixel values are somewhat related to each other. They differ substantially from the pixel values of this area where it is showing of the wall, right? So these images have some kind of a spatial correlation in a local neighborhood. Now, when we flatten these images, we lose this information. So this is another reason which prohibits generally the use of only fully connected layers when dealing with images. So now this is, I think, very clear, right? What is parameter explosion here? So suppose this is an image, okay, and the image can be a very high dimensional image. So let's consider a simple task of classifying an image into one of the possible 1,000 classes. So this 1,000 classes is nothing new. We have this one ImageNet data set, which has millions of images, and they are being supposed to be classified into one of the possible 1,000 classes. Now, let's just consider a simple one-layer neural network. That means we will take the input, we will pass it to the layer, we will apply the activation function, and then or the softmax, and then we will do some kind of prediction there. Okay, so this is not realistic, but just for explaining purpose. So now here for this network, what will be the shape of the weights? So suppose the images are 200 cross 200. And there is also a 3 here, which should be there. So this is right now we are working only with grayscale images. So it will be 200 cross 200. But if you go to these RGB images, then they will have 3 channels. You multiply with 3 further. Okay. And now if you look at the weights vector for this only one layer neural network, it will happen that it will be 200 cross 200 cross 1000. So this will be the dimension of your weight vector, which is like almost 40 million parameters, right, to be learned here. And the bias shape is, however, just dependent on the size of the layer, which is only 1000. But if you look this, right, so as we increase either the dimension of the images or the dimensions of this hidden layer of or the number of neurons in the layer, these parameters will uh, be like they will also increase by a huge value. Okay, and this is only for one layer neural network. Let's consider a two-layer neural network, in which case we have one hidden layer whose dimensionality is 1000. So now we can treat this layer as a hidden layer with a dimensionality of 1000, and then there will be another layer which will be handling this 1000, the output of this 1000 dimensions from this layer, and will be then taking it, processing it, and then classifying into one of the 1000 classes. So here, in case of two-layer neural network with one hidden layer dimensionality is 1000, the total number of weights to be learned will be W1 plus 1000. So this is the value of W1. So this plus 1000 cross 1000. Okay, and the bias will be this bias plus another 1000 dimensional vector. So the summary of this slide is that as the size of the images increases and as we move from grayscale to RGB, then we to process these high dimensional data, we need a lot of such layers with a high number of hidden neurons, and all these will result in a very large number of weights and biases to be learned. And to learn such high number of weights and bias in any model, we need a lot of training samples and lot of computing resources, which may not be feasible always. So this is another reason why we do not prefer using fully connected networks when dealing with images. We use it in combination with convolutional layers, but we don't directly go for the fully connected layers. The another reason is obviously that we lose this spatial correlation between the pixels in a local neighborhood. So the alternative is using this convolutional neural network. So what does this mean? A network which will be now having convolutional layers. And the aim is that these layers are designed such that they look at local regions, okay? And they maintain this spatially correlation between these neighborhood pixels, okay? So what it means, suppose this is an input image, and this is the output after applying a convolution filter, which we will see in the next slide. So if you apply a convolution filter over this input image, this will be the output. And if you look at this output, you can see that here in this, so these are the two bounding boxes, right? The squares that is showing the mapping. So this big square is now being mapped to this small square in this output activation map. And one can easily see the correlations being maintained between these pixel values here, right? So the darker pixels here still remain dark related to the neighborhood. Okay. Similarly, when we apply further convolution over this image, we can see that the size has decreased, but still you can see that some kind of correlation between neighboring pixel values is being still maintained. So these pixels which are lighter in, which are more white as compared to the neighborhood pixels, the pixels belonging to the book, is still somewhat maintaining a high content of white with respect to other pixels. So this is just for example purpose. This is not how the activation map look, but this is just being presented here to explain the idea of convolutions. And then once we have reduced this high dimensional vector to some manageable low dimensional 2D vector, 2D array, we can then use a set of fully connected layers to finally classify this into one of the desired classes. Now let's look at what is this convolution operation. So I hope that we have already covered this, but this will be a small revision to it. So suppose this is an image here, okay? And this is our convolution filter. So remember this, the weights of this convolution filter will be same for at each and every location of the input image, right? So what will happen, this is a 3x3 filter and this image is 6x6. So first this 3x3 filter will be then up convolved over this first 3x3 bounding box here, right? This 3x3 square, and the output will be stored here as 1 square, this one purple. Then we will slide by a, so here the stride is 1, so then we will move shift by 1 cell towards right, and then we will consider this particular square. Okay, and we will convolve this with the filter to get the next value in this, which will be represented here. Similarly, we will further move one step and then we will convolve this filter with this 3x3 patch here, and the output will be stored in this third square. Okay, so this third square is now representing the output of this, applying this convolution filter over this patch. Okay, so then we will take one stride further and then we will again apply this filter to this last patch here and get the value in this last square. Since we have covered all the rows, now we will shift this filter, that is we will move shift in the downward direction by one step, and we will be this particular patch of the image will be convolved with the filter and the output will be stored here. Okay, so this is how this convolutional operation is going on. But you can see that even though we are dealing with such a high dimensional image here, the set of weights to be learned is fixed because at each location we are using the same set of weights. Okay, so this has reduced the need for such a high number of weights to some manageable number of weights to be learned. And the second thing is that it is also resulting in a reduced size of the output, assuming we haven't padded it, so there is no padding. If there is a padding, then we can definitely get the same size of the image, or we can even get a larger size depending on what it is, right? So right now we are not assuming any padding here, so, and we are convolving with this filter, so the size of the output is smaller in comparison to the size of the input. Let's look at it in a bit more detail. So this is an image of resolution 32 cross 32 cross 3. The 3 is representing the RGB channels here. And the idea is that when you will use the convolution filter, it will preserve the spatial structure of the image. So let's try to convolve this image with a filter of dimension 5 cross 5 cross 3. Remember, this last dimension will always be equal to the number of channels. These are known as channels. So the number of channels in the input. So if it was 5 here, then it has to be 5 here. If the number of channels in the input is 10, then the size of this filter will be 5 cross 5 cross 10. So this 5 is representing the size of the kernel here, right? So basically what it means that we will be looking at a 2D array of 5 cross 5 size in the image. Okay, and this is the third dimension here is fixed, and that should always match the channel dimension of the input. Now the filter will be convolved over this input image, and using simply, that is, we will slide over the image spatially, computing the dot products, and that product value will then be stored as in the output. So let's look at it in detail. So this is an image 32 cross 32 cross 3. This is our filter 5 cross 5 cross 3. And this filter has been applied at this specific location in the image, and this will result in a single value. And the single value is being computed as like the multiplication of each of the corresponding elements in the filter and the image patch considered, and then adding it to a scalar value. So a simple question can be like, how many dimensional dot product has been done? So there are total of how many elements are there? 5 cross 5 cross 3. That is 75 elements are there. So there has been 75 multiplications, and then the value has been added, and then one additional bias term has been added. So these many multiplications and additions have to be done in order to get the output value at a single location in an image. So once we convolve this filter over the entire image, we will get an activation map of size 28 cross 28 by 1. We will come to how this 32 cross 32 has been reduced to 28 cross 28 in the next slide. But till then, just assume that, just trust me that this feature map is going to reduce to this activation map of size 28 cross 28. The number of channels has been reduced to 1. So when we convolve this with one filter, we are just getting one output here, right? To get multiple channels in the output, we need multiple such filters, okay? So now if we convolve it with another filter, this color difference here shows that this filter is different from the filter in the previous slide. Okay, we will get another activation map of the same size, that is 28 cross 28 cross 1. So as we will keep on increasing the number of filters, we will keep on getting the number of activation maps in the output. And stacking all these activation maps together will form the output of applying those many filters on this input image. Okay, so here the final, after applying 6 filters of size 5 cross 5 cross 3, the output shape will be 28 cross 28 cross 6. Till here, is everything clear? If there are any questions, please feel free to ask, or I'll proceed further. Okay, then let's go to the next slide. So now this is how we can have a series of convolution layers. Okay, so we have this input image, we apply a set of convolutional operations, and then we follow this output of the convolution by some activation function, which is a nonlinear function in general, which can be like a ReLU or a sigmoid or a 10H, and then we get the final output here. Then this output is being further convolved and passed by an activation function to result into another output. Okay, and this will keep on happening. Okay, so to move from this image to this image, we needed 6 filters of 5 cross 5 cross 3. This 6 is exactly the same as the number of channels in the output. To move from blue image or blue activation map to the green activation map, we needed 10 5 cross 5 cross 6 filters. So remember, this 6 is same as the channels in the input image. Number of filters 10 is same as the number of channels in the output here. Okay, and so on. Now comes stride and padding. So we noticed here that the size was decreasing from 32 cross 32 to 28 cross 28, and then further it decreased to 24 cross 24, and so on. So how does we actually compute the size of the activation map? And so far we have considered the stride as 1, right? We just shift it by 1 in the right direction or by 1 in the downward direction. What if that stride is greater than 1? And how can we solve the problem of this decreasing resolution here from 32 to from a resolution of 32 cross 32, it decreased to a resolution of 28 cross 28, which further decreased to 24 cross 24. So how can we even fix this issue of decreasing resolutions? So here comes the concept of stride and padding. Suppose this is our image, okay, and this is a 7 cross 7 image. And we are convolving it with a filter of size 3 cross 3. Okay, for now, assume that the input has only one channel, so the filter will also have only one channel. So what should be the output of the, so what will be the size of the output? I have given the formula here, but it's still okay if anyone wants to do it. So what will happen is that first you will convolve it here, take the dot product, add the bias, you'll get a term. Then stride by 1, then you will again take a dot product, add a bias and 1, and so on. So there, how many times you can do it? So we can do it exactly 5 times here, right? And then similarly 5 times here along the y-axis, resulting into an image of size 5 cross 5 instead of 7 cross 7. So the output side is given as n, where n is the dimension of the image, minus f. F represents the dimension of the filter using, divided by the stride. Sorry. Here stride is 1, so it's 7 minus 5 divided by 1, which is, sorry, 7 minus 3 divided by 1, which is 4, plus 1 equal to 5. So this will result in 5 cross 5. If I have a stride of 2, then it will be 7 minus 3 is 4, 4 divided by 2 is 2, 2 plus 1 equal to 3. So it will result in an output of size 3. Okay, and so with the stride 1, we will get a 5 cross 5. With the stride 2, we will get 3 cross 3. With the stride 3, Well, it's not even a number. It's not even an integer number. It's something 2.333, which makes no sense, right? Which means it will be basically 3, right? Because some of the cells we have to leave unconverted. What can be the solution? The solution is that we can either make the size, this n minus f, to be divisible by this stride, and that can happen by adding some false rows and columns in this image. Okay, and that's where the padding comes. So now what we can do is that we can increase the size of the 7x7 image by a zero padding. It means that add a row and column on both left and right and up and down of this image and pad it with zero, which means nothing but you are giving a thick black border, right? But what will happen is that this has changed the size of the image from 7x7. Now it has become a size 9x9 because we have added 2 rows and 2 columns. So the changed size of this image is now 9x9 instead of 7x7. And now when we try to apply this formula here, it will be what? 9 minus 3 divided by 3, which is equal to 3 plus 1. Sorry, which will be equal to 2 plus 1, which will be equal to 3. So this will result in an output member of size 3x3. So how to change this? So instead of n, here, if you are doing some kind of padding, it will be n plus twice of the size of the padding. So here it was 1. So it means 1 left, 1 right. So it was 1. So it will be n plus 2 into 1, which will result into n plus 2 minus f. F is the size of the filter. Okay, so this is clear, or is there any confusion here that how did we got how this formula is working and where the stride and padding will come into place? So now if we pad the 7x7 input and apply a stride of 1 and we pad it with 1 pixel border, so the resultant image will be of size 9x9. And we have this 3x3 filter, right? And a stride of 1. So what will be the shape? It will be 9 minus 3 divided by 1 plus 1, and that will result in 7x7 output. So the output of the feature map will remain the same as the output of the input. Isn't there a provision in which I can let anyone join this session on their own so that we are not interrupted? Okay. So just to summarize what we have seen so far, so what is the size of the input, right? So the input can be written as the size of W1 cross H1 cross D1, right? Where H1 represents the height, W1 represents the width, and D1 represents the number of channels in the input. Now we need 4 hyperparameters. That is the number of filters are required. What is their spatial extent? That is F, that is the size of the filter, the stride, and the amount of zero padding P to be done. So this will produce a volume of size W2, H2, and D2, where I think this we can do it, right? So D2 will be equal to the size of it will be equal to the number of filters used. So D2 will be equal to K. W2 will be equal to what? W2 is given by this formula, right? This formula. N plus 2P minus F divided by stride plus 1. So W1 minus F plus 2P divided by the stride plus 1. Similarly, height will be H1 minus F plus 2P divided by S plus 1. Okay, so this is width and height are computed, width and height are computed equally by symmetry. In case the image is not a perfect square, in which case it can be simply like 224 cross maybe some 256. Then in that case, the width and the height has to be computed this way, right? Where because that will not be same. If it is 224 cross 224, you can just compute the width and that will also be the height. Now, with parameter sharing, what has happened, right? So with parameter sharing, so the size, what is the size of the filter we have learned? It is F. So each filter has a size of F cross the number of channels in the input, which is D1, F cross D1. And how many filters we had to learn? K. So the total number of parameters now need to be learned is F into D1 into K weights plus how many biases? K biases. So these are the total number of weights and biases to be learned in case of convolutional layer. And this will turn out to be way smaller than what we would have learned if we would have used a fully connected layer. Okay. In the output volume, the depth slice of size W2 cross H2 is the result of performing a valid convolution of the dth filter over the input volume with a stride of S and then offset by dth bias. Okay, so what does that mean? That the dth channel in the output is actually the result of applying the dth filter onto the input image. Okay, so this is a brief summary of what this convolutional layer is. What should be the size of the input? If the size of the input is known and these four parameters are known, then you can easily compute the size of the output, which will be W2, H2, and D2. And the number of parameters which this particular convolutional layer needs will be F into D1 into K, weights, and K biases. The other important layer which we're talking about is pooling. This generally comes in downsampling. Okay, so what happens is this pooling layer pool is a downsampling operation, and this is typically applied after a convolution layer. The general idea or the intention behind this is to downsample the size of the output to some manageable size, which does some spatial invariance. In particular, we can use the max pooling or the average pooling. So in case of, suppose this is an image, okay, this colored coded image, and we want to downsample it. And let's say we are using a filter of size 2 cross 2. What it means, we will look at this 2 by 2 patch here, and the maximum value in this 2 by 2 patch here will then be considered and will be put here as an output. So this is the darkest color, so the darkest color will come here. Next, it will come as this 2 by 2. So it is with a stride of 2, let's say. So here in this 2 by 2 block, what is the darkest color? The darkest color is this, so this will come into picture. Then for this 2 by 2 patch, this is the darkest color, so this color will come here. So in this way, though this shape has an image of 6 cross 6, after doing the mix pooling operation, it will have a shape of 3 cross 3. Similarly, instead of doing the max operation, we can also do the average operation. And that average operation will be the sum of all these pixel values in the patch divided by the number of pixels. So here, when we will do the average of all these 4 colors, it will be some color darker than this, but lighter than the other 2. Okay, and so on. So the idea is that we want to downsample the feature map for reducing the number of parameters as well as efficient processing. This downsampling is definitely resulting in some kind of loss of information, but not much, because here we have taken into account the maximum pixel value. Here we are taking the average value. So there is a loss, but then there is a trade-off that we have also decreased the size of the image, and the loss is not very significant here. Okay. Yes. Sure, we can talk about it. So after this presentation, I'll be showing you an implementation part, and then we can play around with. Yes. Yes, so I'll show you that as well. So thanks for this question. So I have not included the specific illustration part, but we can do it in the session itself. So just 2 more slides, and then we will look at the implementation part. Okay. Any other questions here? Okay, I forgot to share that. Okay, so let's continue. So this is just a pooling operation to downsample the feature map here. And then we have this fully connected layer. So once we have reduced these high dimensional images to some manageable sized vector, we can flatten it and then we can have a set of fully connected layers. We can either have one or two, or depending on our need, we can add on fully connected layers to get the final output. So this was the map which we got from here, the output map, which is then flattened and then connected to certain fully connected layers. This will reduce the number of parameters by a large margin, instead of directly putting the fully connected layers to the original input image. So an example of CNN will be that this is an image of a car, and we want to classify this image into the, so there can be multiple classes, and we have to classify this image with the right class. And now we give this image as an input to a model which is comprising of multiple convolutional and ReLU layers. So we first apply a convolutional layer, then apply the ReLU layer, then convolution, ReLU, pool. Pooling layer is basically, it can be a max pool or an average pool. So we have a pooling layer and so on. So we have a sequence of convolutional layers followed by an activation function. Then somewhere in the middle, we have some kind of pooling layer to downsample these feature maps. And then when we get the final low dimensional vector or some manageable 3D tensor here, we flatten it and connect it to certain fully connected layers to finally predict the probability of each class. What I mean is, by probability is that what is the probability of this image being a car, what is the probability of this image being a truck, and so on. And the class with the highest probability will then be considered as the predicted class of this image. So in this output here, we can see that class car has got the highest probability. So the model will label it as an example of class car. Okay, so far we have seen convolutional networks with a brief introduction to what convolutional layers are, how do we compute the size of the filter and the output map, followed by pooling layers, and then a small example showing how this convolutional neural network looks like. Now let's go to the implementation part. So I'm not sure how many of you did attend the last session, but if you have, then you remember that in the last session, we solved this problem of image classification on MNIST dataset. So MNIST dataset is basically the set, a data of these handwritten images, of these digits. So these are the handwritten images of 7, 2, 1, 0, and so forth. And these images are then being annotated with the right class, right? So this is an image of character 7, and it is being annotated as an instance of class 7. So this data set has 10 classes, class 0, class 1 up to class 9. And each class has 6,000 training samples. So these training samples, what I mean is that these will be the 6,000 images, and each image will be a image of handwritten character of that specific class, right? Give me a minute. Okay. Okay, so this is MNIST dataset. In case you don't know yet, I'll suggest you to go through this dataset. It is easily available in this torchvision.datasets, and it is a widely used dataset and also the beginner dataset. So this will be very good with if you explore this dataset and start working with it. Like, this is the most basic dataset anyone uses in deep learning. Okay. Now let's talk about the model architecture. So how to create a model architecture? So we here now creating a CNN, and this CNN is okay. So when we are getting the CNN, so it has this one convolutional layer, and the images are of size 28 cross 28 cross 1. So here the input channel is 1. The number of channels in the output I want is 64. So it means we will be having 64 filters here. Now the size of the filter is 3, which means there will be 64 filters of size 3 cross 3 cross 1, because the input channel is 1. And 1 here represents the stride as 1, and there is no padding. Similarly, we have this convolutional 2 layer, which is again taking 64 channels as an input, and the output of this layer will be an output with 32 channels, which means this layer is offering 32 filters, each of size 3 cross 3, with a stride of 1 and no padding. And then whatever we will get the output, that will be flattened using this fully, and then the size of this feature map will be 800, and we will be connecting it with some fully connected layer with hidden neurons as 256. And then there is another fully connected layer which will take this input of dimensionality 256 and will produce an output of dimensionality 10. Okay, now here you can see some pooling layers. So what that does is that please from next session try to join on time. Okay, so here we have these pooling layers. So these pooling layers will make sure that whatever the feature map we are getting is being downsampled. So what I can do is, for ease, I can just start printing the shape, and that will give you some idea about it. So give me a minute and I'll put it here. Okay, so the network is clear to you, right? So in this network, we have this convolutional layer, which we apply ReLU. Then we pass it through a max pool layer. Again, another convolutional layer, followed by ReLU, and then max pool layer. Then the input is being flattened and given to a fully connected layer. And the output of this fully connected layer passed through ReLU, which again then goes to an input to another fully connected layer. And the output is then finally being used for prediction. So what will happen is that whatever the output of this map will be, we will apply the softmax, and on the softmax, on the top of that softmax, the loss function will be applied, which will be maximizing the log likelihood and or minimizing the negative log likelihood, right? And once this is done, during prediction time, the class with the maximum probability will be predicted as the class of the image. Okay, so this is the model architecture. Convolutional layer, max pool, convolutional, max pool. So when I'm telling you convolution, it is convolutional plus ReLU here. Okay, so convolutional ReLU max pool, convolutional ReLU max pool, fully connected ReLU, fully connected, and that's it. Now, yes. Yeah, so you okay, so if you do it one time, that is also okay. So here is the trade-off, right? So as you increase the number of parameters, you get a better performance. So there is something called as the capacity of the model. If your model has more number of parameters than it needs, then in that case, the model, you can reduce the size. Similarly, if the capacity of the model is less than it needs to do the task, in that case, we need to increase the size. So as an example, maybe what we can do is, for now, I can even reduce this one set of layers. Okay, so let's do that as well. Yes. Yes, so that is just for getting the right performance. So that is known as the architecture, finding the right architecture for your task. What I mean by that is that these are certain kinds of hyperparameters. You basically do in it and you see it that okay, adding another layer is giving you some benefit over the previous layer or not. How many layers are needed in the network, right? These are certain open questions still, and people still go with the heuristics and by experiments and find the right architecture so far. And to show what it means is that I can just start doing one thing. Give me a second. So let's change the architecture for now and just consider one set of convolutional ReLU max pool and a fully connected layer. Okay. And let's look at its performance. Okay, so convolutional ReLU max pool. Flattened C1 activation. Okay. So this has to be definitely 10. This is 64 into 25 by 2. Okay, just give me like I need to see the output here so that we can then fit the right thing. So it is going to give an error, but then just fill it up for me. We need to see the size of the flattened array. Yep, so it's 10816. Maybe in that case, okay, that's a very huge number. Okay, so what I can do is that I can use a max pool of maybe size 4 here. It's not going to perform good, but let's try. Okay, so just to show you the result first. So this is the input 128, 1, 28, 28, right? The size after applying the convolutional is 128 cross 64 cross 26 cross 26. This is clear, right? Because we had 64 filters and we did a convolution with 3 cross 3 filters. So that has reduced the activation map size from 28 to 26. Then a max pool, and the max pool size, the filter we are using for max pool is 4 cross 4. So it has reduced it further by the 6 cross 6. Okay. And then it is being further flattened. So this is basically 64 into 6 into 6, which is equal to 2304. And then it will pass through one fully connected layer of 2304, 10, and it will give the output. So since this is clear, I'll just comment it out. So now the model will start training. It will take some time. Maybe I could reduce the batch size for faster results. Is it okay? So give me some time, it will run. So what? So the reason is that I used multiple layers here is to get a better performance, because even classifying an image of size 28 cross 28 cross 1 is a challenge. So this model with only one set of convolutional and ReLU layer may not be sufficient to this. And this was the reason where we stacked it. So if you look at this very popular convolutional network as Linet, it has 2 convolutional layer, 2 max pool layer, and a 2 fully connected layer. So it's a 5-layer neural network. And that is like that gives an accuracy of almost 97 to 98% on the test data set. So here you can see the accuracy is after one epoch, it's 67%. Maybe I can just run it for, so after maybe 2 or 3 epochs, we will stop here. And then we will try it by adding these commented outlets. Maybe I can just start editing it for now. Do you remember what was the size here before? Anyone remembers the size? I think it was 800. Let's try. Okay, so the accuracy is like going from 66.9 to 68. Okay, now let's just stop it uh, and try it with this more layered network. So as we increase the like you will see it in future lectures that as the size 128 cross 128 and 800 cross 256. So as you will see later in the lectures that as you increase the size of the model, the performance definitely increases. But then there is always a chance of overfitting, which happens that you do not have the sufficient data for generalizing its the performance of the model over the unseen data, and the model has somewhat memorized the data. So the size of the model should always be somewhat in relation to the size of the data you have, so that you can learn the model correctly with good generalization capabilities. And generally increasing the capacity of the model helps in attaining a better accuracy. Yes. Okay, so here's the thing. So all these optimizers actually try to help you find the local optima, right? And that local optima depends on the kind of the function being modeled by the architecture. So this architecture is some sort of the hyperparameter because each architecture can map a certain set of functions to the input, right? And the optimizer is just making sure that whatever the model you are using is able to find the right optima. Right optima is a wrong word here, maybe the local optima. Okay, and that should be locally good. Now these optimizers actually try help you in achieving that local optima. So when we talk about different optimizers, these different optimizers might help you in achieving a slightly better local optima, or they might help you in achieving that optima in a faster manner. But it will hardly be a case that using an SGT you are getting a performance of, let's say, 60%, and using an ADAM you are getting a performance of 90%. That may be a very rare case. Generally, all these optimizers converge you to somewhat similar performance, though they have an like they might be good with respect to the time you are taking in achieving that local optima. Generally, ADAM is a very well used optimizer, but you can still achieve the similar performance as SGT with SGT using the right momentum and learning rate. Did I answer your question? Okay. So here, just adding one more layer of convolutional and a fully connected layer, we started with a performance of 96.5 after one epoch. So increasing the capacity of the network is definitely helping in achieving better performance. So this is one. And then the next question we had is regarding the pooling layer, right? How is it working? So I think you saw that after the pooling, the feature map size was reduced. But just to see how it works, what I can do is I'll try to print the value before pooling and after pooling. Okay. So let's print here. It's okay. And let's stop here. It will not take much time. It will just stop after one iteration itself. Yeah, the issue with collab is that it is slow in comparison to your local system. Yes, yes. Okay, so here's the thing. Actually, all these models. Okay, I come to your question. Just we have an input here, so maybe we can stop you, and then I'll definitely come to your question. Okay, so it doesn't take exit, it seems. Don't they allow exit in collab? Okay, I just need to rerun it. It crashed. Okay, so these architectures you're talking about, I think even not Google net is, you're talking about Inception, I guess. So that even Inception is not a new network. We even have a network which is better than that. So where is that FC is here? Okay, so just a minute. Okay, I'm still stuck at this thing. So once this is done, I'll answer your question. Okay. Levels. Okay, let's come to your question. So when you talk about these networks, right? So there can be so many networks in all the domains. So if you talk about classification, we have ResNet, VGG, AlexNet used to be the initial, the first one. Then Google, even in Google Net, we have so many Inception 1, Inception V1, Inception V2, and so on. So all these networks are good. It depends on the kind of data you have, right? Because all these networks have different kind of parameters. And for example, with ResNet, right, VGG has the most number of parameters. ResNet has less parameters because of its using this. And also, in case of ResNet, you have these what we call that, the skip connections. I was forgetting the name. So in ResNet, you have the skip connections, and because of which the gradient backpropagation is good. Even as you increase the depth of the network, then also the layers in the very beginning can get the gradients, right? In case of inception, you have multiple loss functions. So different, you get the computer loss from different parts of the network, right? And there are so many networks, like for example, the mobile net, which has very few number of parameters. So all these networks are good. To start on your data set, you need to decide what is the size of your data set. If you have a large size of the data set, you can definitely go for larger networks with large parameters like ResNet. Even ResNet has like ResNet 150, ResNet 50, ResNet 1000, and so on. So many models are there. So before, I think that using these architectures may not be a very different. It mainly depends on your data, and you should choose the architecture depending on the size of your data and the tasks you have to handle. Because using different architectures on the same data, the performance may vary, but it may not be very significant. I generally prefer ResNets. ResNet 18 and ResNet 52, they are really good. They do good on most of the data sets. Is that okay? Or Yes, that's true. I see. Yeah, so that's true. But we still do some kind of work with ResNet. And the good reason about ResNet is that they have this skip connections there, right? So using which the gradient backpropagation is very good. So again, it depends on your task at hand. There's not much. I'm not sure if these models will result in a very drastic performance difference. The performance difference will not be that significant. You just need to find the right set of optimizers and the hyperparameters with each network to get the desired performance. So the one of the main issue with computer vision is that there are a lot of hyperparameters. Like finding the right architecture is one of them. Then training those architectures using the right set of the learning rate and the optimizer, the momentum is another thing. Finding the right loss function, then the number of epochs for which you have to train, that itself is an hyperparameter. Though we try to look on the performance of the validation set and then try to find the smooth point where we should stop. Um, but again, all these are certain set of hyperparameters which one can be confident about only after doing the experiments. Um, for me, my understanding is that all these architectures are good, and like I have worked both with GoogleNet and ResNet, and for me, they both are good, and their performance does not differ much if we are able to find the right set of hyperparameters there. Yes, in terms of the number of parameters versus performance, I think Google Net will win because they've reduced the parameters drastically and is still achieving the similar performance. Okay. So here is the max pool thing I wanted to show. So this is an array of 10 cross 2. So here we used a max pool of 2 cross 2. So if you look here, this is 2 by 2. So the maximum value is this. So that is being stored here. Similarly, let's look at the next 2 cross 2. So this is next 2 cross 2. And here the maximum value is 0.26. So that is being stored here. Similarly, let's look at the next 2 by 2. So this is 0.29, 0.31. 0.20, 0.10. So the maximum is 0.3157. So the maximum value will be stored here. Okay, so this is how it works, the max pooling part. Instead of max pooling, you can also have the average pooling, in which you will take the average of these 4 values and store it here. So this has definitely reduced the size of the feature map by 4. 2 in the x-axis, 2 along the y-axis. Total a decrease of 4. Like 4 times the output is smaller than the input.